Hello and welcome to the Conscious Design Podcast. I'm your host, Ian Peterman, and I help turn product ideas into sustainable seven-figure businesses. Join me for another episode where sustainability meets innovation and business savvy. Today, I'm excited to have Don Weatherbee. He's the CEO of Regenx, where they've developed a new technology for recovering precious metals from electronics at end of life, which we need more of. Welcome to the show.
That's what we're here for.
Perfect. Yeah, so everybody loves a good origin story. So let's dive a little bit back. How did this, recycling precious metals is the thing we've been trying to figure out for a while better at. How did this come about getting this technology?
So Regenx has a fairly long history. And where we started out is we were one of your traditional junior exploration companies. Those companies that buy properties and dig holes, try to find new resources. And so I joined in 2015. And at that point in time, they had just sold one of the properties and still had another property. And we sort of re-looked at the business model and said, digging holes in the ground wasn't offering a lot of value. And so looked at what could we do? And we had an opportunity to acquire some material processing technology. So this technology was intended to capture gold from tailings in water scarce environments. And so it was supposed to reprocess old tailings because what was deposited as waste 50, 100 years ago could be economical today if you're with new technology. That morphed itself into going into e-waste because different people started to hear you could process materials. They bring you other materials and say, can you do it to this? Which brought us to e-waste. And then it brought us to the attention of Davis Recycling, who was looking to do something with diesel catalytic converters and sort of showed us that there was a niche out there because these diesel catalytic converters, they're built from a silicon carbide substructure. And the traditional recyclers, which are smelters, don't like that material in their furnaces. And so it's a product that wasn't getting recycled. So he asked us what we could do with our technology. So back in 2020, we started doing lab testing. That morphed into a pilot plant, worked into design, and then so we've just commissioned and have started operating our first module of our commercial plant down in Tennessee.
Now, when you're talking about, because most people think about like catalytic converters is not really rich in precious metals and things like that, but do you talk a little bit about, because you started in e-waste and a catalytic converter is not e-waste. How do you tie those together?
It's not, but it is the same. So in e-waste, you have primarily gold is thinly coated on circuit boards or pieces like that. So there's a thin coating on these structures that you're trying to break apart. And because it's a thin piece, most of the times you have to do it chemically or with smelting. You either has to melt it or leach it. And so when you look into catalytic converters, it's the same basic structure. The catalytic converter, inside the guts of it, is a honeycombed structure for the diesel that's silicon carbide. On that silicon carbide is a thin layer of platinum or palladium that's deposited on those. So again, the same technology is you can't just crush this down and get the metal. You either have to melt it or you have to leach it chemically. And so it's about separating two pieces to recover the precious metal.
Got it. And so does it really matter, palladium, gold, does it matter as much? Like how, with this technology,
With our technology, we're focused more on platinum and palladium. We could do gold. There's some, and we also focused in on the diesel because they don't have rhodium. A lot of the gasoline ones have rhodium in them. And rhodium's a little bit harder to separate. So each of them have separate points where they like to separate. We're using the same word there, but under different circumstances, for one piece will come off, and then after you tweak it a little bit, the second piece will come off. So they're about selectivity in how you have to process them to get them each to be able to be recovered from the material.
Now, you mentioned economics, right? And things that would have been considered garbage 20 years ago or more now make sense to possibly recover. Is it just purely a technology level? Is it that gold and palladium and all these have finally gone up enough in value and demand? Kind of,
it's a
what
little
are
of
you
everything.
seeing?
Partly it's the price going up. Yeah, the price going up always helps and makes some things do that. But it is the technology. It is about getting the technology right at better and better cost points to be able to handle the need for the economics to make it work.
Now, technology wise, could we, not everybody's super familiar with this, dive a little bit into how smelting, everyone can understand that pretty easily, right? You melt it, you get it to a temperature and it starts to melt off. But chemically, how does this process work for the average person?
It's called leaching, hydrometallurgic leaching, as the technical term there.
Yep. Wikipedia that later.
So what it effectively is just using a chemical that turns the solid element into a liquid version. And so what it is, and it's not melting it into liquid. It's taking a liquid chemical that grabs the elemental, the ions of the metal, and attaches it to its liquid version, which then becomes a solution. So you've turned it from a solid to a liquid, and then we use another chemical process to drop it out of the liquid back into a solid form.
Right. And so the obvious benefit that is you're not heat stressing, you're not causing heat damage to the rest of it. You're able to just pull away.
In the heating, you're not really causing any damage because of the heating point.
Well, I mean, like a PCB board starts to burn.
But the precious metal will mix back between your molten and your solid state without any stress on it. But it's about the energy used. So it takes a tremendous amount of energy to use a smelter to get your conversion versus a chemical process.
What is that
difference?
Well,
what we know of is that a smelter will create 1,500 kilograms of CO2 for every ton it processes. And we're minimal amount of CO2.
Right, because you're not generating any heat. You're using a chemical mixture.
Yeah, there is a little heat reaction in our piece, and we have to heat up our chemistry, but it's not the same as bringing something to a metal's melting point that's in the thousands of degrees type thing.
Right. So are you able to capture more material? Like if you had the same exact part, let's say this catalytic converter, right?
The smelter will pretty much capture 100%. We're in the 97, 98%. The real reason that is because we change states and we change it to a liquid, and then we have to separate out the solids like the honeycomb, silicon carbide. Getting something to separate completely from a liquid to a solid is never perfect. I mean, you never get something, when you're trying to separate water and a solid, there's always some moisture kept in the solid. So we lose a little bit on that in that base transfer.
Okay, so but if you're at 97%,
it's minimal.
Very close.
Yeah.
What does obviously there's a cost difference in this too, because if you're trying to heat something up, that's a lot of CO2 and energy. How does it cost compare?
So on a operating cost, we're more expensive than a smelter because it's a fairly simple process of just putting like natural gas or something like that just to supply the energy. When you look at it holistically, smelters are huge and hugely capital intensive. So it all depends on what you consider the cost of a smelter and how long into its life cycle it is on the true cost balance versus whether or not you're looking at the fixed sunk costs or you're just looking at the operating costs. But on a pure operating basis, a smelter is cheaper, which is also why we looked at what product were smelters not trying to have. So moving into the diesel was we're looking for a niche that wasn't being recycled because it wasn't, the dominant recycler didn't want it. So there's a market there for you to go after where you don't have to be at the as cheap as a smelter.
Right. Now, you mentioned footprint too. Smelters are large. How small of a footprint are you able to operate in a smaller facility then?
Yeah, we're in about, right now we've done module 1, but we've got space for 4 modules in a 20,000 square foot area.
That's really small.
Yeah.
I've been through a smelting place. They're very large.
Yes. And so that would allow us to process 10 tons a day of feedstock.
Wow, okay. And when you say 10 tons, is that 10 tons in or 10 tons?
10 tons in the feedstock, the powder. What the take is the catalytic, our partner Davis takes the catalytic converter and takes the inside honeycomb out of the shell and grinds it down for us. And so that powder that he gives to us is what our feedstock is. And we can do 10 tons of that. We will be able to do 10 tons of that powder.
Okay, so now you're talking about grinding it down into a powder. Is that necessary, or does it just make it more efficient? Like,
It makes it much more efficient because for our leaching to work, we want the liquid to touch as much of the solid as we can. And so if you've got it in bigger pieces, well, it gets hard to get into all the little nooks and crevices. It takes a lot longer to do that. Whereas if it's powder form, you're instantaneously touching more and more of the points.
Guys, it's an efficiency.
Yeah. And also, because it's going into a liquid, we need to stir it. So if it's in a powder form, it's much easier to stir and move and then big chunks. Like anytime you try to move big chunks, you're not going to get it to come out of your reactor very smoothly.
Yeah, mixing chunks never is easy to do. Now, what comes out when you do this process, where you put the solution in, it pulls out whichever material you're wanting, and then you have this leftover stuff. Is there any use for that? Can you process it again? Let's say it was coated in 2 different metals. Is it possible? Or
it's a silicon carbide base. So it's an inert material that there are some commercial applications that we're pursuing with it. And eventually, silicon carbide itself is a material that's in demand. So we're also working a way to try to clean it to get back to having some silicon carbide that you could reuse in the marketplace too.
Okay, because that's the base material that gets plated, and so you're removing the plating, and then now you're going after how can we turn the leftover back into, if they wanted to make some more catalytic converters out of it, even just have that material.
And so silicon carbide is a huge piece also in a lot of electronics, the electric vehicle, all the energy future has a lot of those pieces too.
And so is that something that you guys are working on directly so that you'll have like a facility that could process both?
Yeah, we're not down that route. We're taking the first part is saying, okay, let's get the precious metals. And then what could we do with the tailings? We've got some opportunities of just letting it be used in some commercial applications, but understanding that silicon carbide is also a resource. We're looking at, we've got some lab facilities and some really good scientists who will also have it on their to-do list to say, okay, get me silicon carbide.
Right. Now, does it cause, because you were talking about it, there's always, there's moisture left. Does that change, I guess, the quality, right? You have this tailings. Do you have that left over, the solution left over, or?
It's minimal. It's minimal in there. I mean, when you're only talking, like, is the process that we get it makes it dry, but the only way to get 100% dry is by really heating something to evaporate all the moisture. And so if we evaporate all the moisture, we're losing that precious metal anyways because it's evaporating. So it's not that it's in a wet state. It's just in that you can't get a completely dry solid. I mean, it's no different than if you dig some dirt of the ground and leave it out in the sun to bake it a little bit. Well, even when you think it's dry, there's still moisture in there.
Right. That makes sense. Now with this solution, are you able to reuse the solution? It's like once you run through and separate out precious and not,
Our
or is it?
base solution, no, it's a one-time use. But we're continuous improvement, and we've got a couple things in the work that potentially will allow us to do reuse.
I would imagine that's probably the most expensive part is making your solution and using it, or
Yes, that is the most expensive part of our process. And that's where, yeah, if we could reuse it would, but there are some costs involved in trying to recycle type thing, which involve your processing time and your efficiencies and all that type of thing. So it's always a trade-off between cost and efficiency.
Hey, it's Ian here. So glad you're enjoying this episode of Conscious Design. If you want the full scoop on conscious design, what it is, how we do it, how you can do it, then check out our book. We wrote it so creative entrepreneurs like you can code social and environmental responsibility right into your brand's DNA. You can download the first chapter for free. Link is in the description. Enjoy the rest of the episode. Don't forget to like, subscribe, and share.
hypothetically, if you were able to reuse that, would you then be able to compete price-wise against smelting? Would that put you in the realm?
We'd have to reuse a bunch of times, but we'd get closer and closer.
Okay, that would be great. That would be awesome if you're able to do that.
Yes.
Very cool. Now, you mentioned, right, catalytic converters is one area. Have you found any other areas where this type of technology is really, where smelters can't really operate?
Yeah, well, we haven't yet, but we haven't really been looking.
Okay. Fair enough.
The potential market in the catalytic converters will keep us busy for the next while type thing. There are some potentials, which there's also the concept of not just catalytic converters for autos, but also industrial. So a lot of times when you see a smokestack, it also has a catalytic converter on it.
Right. Okay. Yeah, that's a lot more. That'll definitely keep you busy for a while. With this, can you do multiple metals, like especially because you're doing some e-waste? Are you able to do?
So we moved away from the e-waste, and partly the e-waste. The biggest challenge in leaching e-waste is that there's a lot of junk in an e-waste board. There's a lot of different metals. There's a lot of pieces that gum up your piece. And we talked about selective leaching, and you can sort of look at the price points of precious metals, and it sort of follows what are the easiest metals to leach. And so if it's an easy metal to leach, it leaches first. For example, copper. So if you have something that has a bunch of gold and copper, all the copper will be taken first. And if you don't have enough leach or releach it, the gold stays. Because, like we said, it's a chemical bond. So you have to have enough molecules to take each piece of the element. And so it takes all the copper first. And unless you have enough of your leaching base pieces, it doesn't have anything more to get. So that's one of the parts that makes e-waste challenging is that you have all these different metals on the same piece, and they all leach at different frequency, for a lack of a better word. That's
now with a solution like this, how does it, I guess for lack of a better, pick what to leach and what not to leach? Like,
So I'm going to talk like a scientist who doesn't know anything, working on just what the guys tell me. And so what it is the leach likes metal.
Okay, but
it likes metal, and it follows the periodic table a bit and says, it goes in order, saying, I like this one, and I would talk to this one if there's nobody else in the room, and only if the lights are off am I going to talk to this one type thing. So it naturally chooses what it's most attracted to, and it will eat all of that, the one it likes the most first, before moving on. And if you've got any real scientists listening, what I've said is probably very wrong, but a metaphor is what has been explained to me.
Well, I mean, that's the important part, I think, for what the scientists do the science version. But that makes sense. So that would make it very. Then you have to have the right amount of solution for, and this is where like e-waste, and I know some guys that work in that space, and they're always talking about how much of a pain it is to work in it, and that makes perfect sense. Where it just
And with your leach, every batch of e-waste is different. So your formula has to be different every single time. So that to know that to get that you've got enough in there.
whereas catalytic converter
Are pretty consistent.
right, because you have the same size or a similar size, and you're plating the whole thing in one metal rather than.
Well, usually two. They'll intercombine platinum and palladium.
Do you pull both off or just one?
Both. They're fairly close in the scale that it likes them both, type thing.
Got it. And then so use it and separate. So you end up with two precious metals and a base material that you're figuring out what to do with. But you're able to get the two precious and now is it powder? Because it's all ground up? Is it?
Yeah. What we've got is it looks like a powder. It's like a black powder. We call it a black powder concentrate. And so we also get some other junk in there. It's not pure. Because like we said, is if there's anything on the table that it liked, it pulled with it. What we then do is with our concentrate, we ship it to an upgrader who then takes it from our dirty concentrate to a 99.9% purity, which is then can be sold in a commodities market.
So that purity, that's the same as mining purity then, right? You're able to match.
Well, the mine moves it right to the same upgrader to get to the same process.
Oh, okay.
A smelter and a miner and all of them have to end up in an upgrader to get the final purity.
So you just go right back into the same, just as if it was mined straight from the ground, and then enters the same supply chain, gets upgraded into a high percentage, and then industry uses, basically.
Yes.
Okay. You're a really nice plug-in too. So there's not much additional.
No.
Really, it's an easy plug-in to the supply chain.
Yeah, and what we're also working with is we're working with some of the smelters because they've got the current feed in the stuff they don't want. They can just divert to us, and we can ship them back the black powder, which is coming out their back end type thing. They can do the work with their customer who's trying to send them this stuff, but don't have to take the inefficiencies in their process.
And something else you mentioned early on was tailings from like the mining industry.
Yeah, so that was what we're not doing much anymore. That was our start in technology.
Right. So what made the shift out of that? Was it just cost-wise? Kind of what?
It was opportunity type thing. Okay. And it's as you move into the e-waste and the catalytic converters, the amount of material you have to process to get larger chunks of precious metals out reduces. In a mine, even in the tailings, the amount of precious metals in there is going to be very small. So you got to process a lot more material to get dollars out the back end. Whereas in the urban mining space, there's a higher amount of precious metals available.
Got it. That makes sense. So really it's there, but just the volume makes it not as good a business.
Not as attractive. Yeah.
Got it. Do you think you guys ever swing back? Like, do you think this technology will grow enough, or is it we need something new for it?
Well, we don't think we'll swing back that much because we kind of like what we're doing, because also with what we're doing is we set up in one spot and this product comes to us. When we were looking at the mining side, our process had to be mobile. So if you're going to do a tailings thing, you aren't going to move these tons of material to a processor to run through. You're going to set them on the mine site, on the tailings site. You're going to run those there. So you had to find new ones, move it to there, move it to the next one. So the infrastructure required is always a little more complicated when you're moving information versus set up in a consistent spot, have the same workforce, have the material brought to you, trucked in, and then trucked out. So, and it's all indoors instead of outdoors.
Right. A big benefit there. Much easier. Much easier. That's awesome. Now, you've had this evolution over the past few years, right? You've gone from getting into new areas with it, and you're not looking for anything else right now, but is there plans to expand, or is this one of those industries where you're like, yeah, we could just be here for the next 30 years and never?
Well, we think we're in an industry that we could be in the next 30 years without any hiccups. We plan to grow in this space, whether we talked about having one module up and then adding to 4 or more in the current facility, but also then looking geographically. We're on the East Coast. Well, does it make sense to put up a plant on the West Coast? Because transportation is always an issue. And so how you connect up with the different areas. So there's opportunities for local growth, national growth, international growth. All those factors are in play.
And with that, as it always makes sense to have a hub where most of your raw material coming in is from. Makes it cheaper to ship, less CO2 and all that. Where are those areas, right? Is it catalytic converters? Is it mostly industrial spaces? I have no idea where car ones go, like a diesel truck. I have no idea where they all disappear to. They just disappeared.
Yeah, so we have a partner, Davis Recycling, who's a major scrap recycler on the East Coast. And so he has a distribution channels in through 13 different states. And so on the auto side, it's end-of-life cars, which end up in scrap yards, crushing facilities. And so those scrap yards, a lot of them will take the different pieces of your vehicle apart. They'll rip off different pieces that are worth different places and recycle different areas. And so he collects from these various scrap yards the catalytic converters.
Okay, because they're worth enough to be worth pulling off the vehicle before you crush it.
Yeah, we don't get our things for free. We have to pay people to actively recycle them, because if we weren't paying for the product, they wouldn't be incentive to do the work to get it for you. So,
is there a possible stream? Because I would imagine car shops that are replaced, like you get your converter replaced. Is that a stream? Is it a big enough stream, or is it?
Well, that's part of also the work we're doing towards working with OEMs. And a lot of OEMs have core programs where send this back to me. So they become the distribution channel and the collection point, which they want to be part of circular economies, but they need to have them processed, which also works in conjunction with the smelters, where you're working all these pieces and finding homes for them to go to bring them back, the metals back into the system.
You're seeing these auto companies, because they're wanting to be part of the circular economy, they're going, hey, send us your cores back. But now they're going, we have a core we don't know what to do with, and we need to finish the circle, basically.
Yeah, and for a bunch of them with the gasoline, they've already had a distribution channel because they brought them back through the smelters and got their product through like that. So the smelters didn't really want the diesel, so they've got their whole system set up to, if there's a home for the diesel, to piggyback that same system.
Right. So that means all the big diesel truck manufacturers and Volkswagen has a bunch of diesel cars. Like all of those were just dead ending because the smelters couldn't deal with it.
Yeah.
Got it. That's a great thing, because I'm sure do they get stored? Is this something that there's piles of them because somebody was like, hey, these will be worthwhile later?
Depends on the group. Some have stored them. Some just get wasted through as if they're a car part that they didn't want to deal with. Like,
just crushed and thrown.
Just crushed and thrown. Just treated for the scrap metal type thing because it wasn't worth my time to separate these pieces. If there's a market, the scrappers are very diligent about filling the supply.
Okay. This is a good space as you get up and people find out about this. The parts will come in. You will have the supply.
That's part of what we're starting to do now is let the industry know, hey, there's a home. Think about these.
You can send them to us. We'll buy it. We'll deal with it.
Yeah.
Wow, that's awesome. Last thing, it's been really interesting. I love all the recycling stuff. It's so interesting how we deal with these things, and we don't always think about it the first time.
Yeah.
People like you have to come along and go, hey, now that you have a stockpile of these, we can do something with it. What's your, I know you guys are planning on growing and everything. What's your long-term kind of growth plan?
Our long-term is in 10 years, we should have 2 facilities, one on the West Coast, one on the East Coast, both operating in that 10-ton range, and be in discussions with international partners on how we could bring this out to different marketplaces.
Amazing. I hope you get there at least, if not sooner.
Yes.
Awesome. Well, for anybody that's interested in contacting, reaching out, what's the best place, website, social?
So we're on most of the socials as Regenx. Our website is www.regenx, regenx.tech, TECH. So we've got that new tech moniker.
Got that. Love it.
And if you're interested in us, we're a publicly traded company. So we're traded in Canada under the symbol RGX, and in the US under the symbol RGXTF.
RGXTF.
Yeah.
Awesome. Always good and good investment option.
Yes.
Looks like you have a corner to market there.
Yeah. We believe we're a good investment option.
As you should. If you didn't, I would be a little concerned. So faith in your own product is good. So awesome. Well, I really appreciate you taking the time to chat through this. And
no, it's my pleasure. I love being able to tell our story.
Absolutely. And that wraps up another episode of the Conscious Design Podcast. If today's episode inspired you to bring your product idea to life and turn it into a sustainable 7-figure business, visit petermanfirm.com or click the link below. Your ideas have the power to change the world, and we're here to help make that happen. Thank you for joining us, and I'll see you on the next episode.